let's discuss the washer method. So I set this up in the last video, we'll set this up again, but if you've watched the video on disks and the one before that on cross sections, that is all building up to this moment. It is just the most complex case of those two cases. So let's say let's just kind of get back in our minds and mentally think about what we did with the washers. So let's say we have a curve. I'm going to make this curve very easy, just a straight line, just for the purpose of being able to try and illustrate a little bit better. So if we wanted to find the volume, if we rotated this curve about the x-axis, I mean, we're rotating like this. And so this would give us a cone, right? This would be a cone because we would be rotating this figure. We'd have this other side of it. Let me try and draw this first circle a little bit better. So when we rotate it, we would have this dotted line down here. Think of a cone. It's a cone. And that was pretty straightforward. And we said to find the area of this thing, to find the volume of this thing rather, the volume is equal to the area times the height. And we said, well, that area, it's a circle, so the volume would be equal to pi r squared times height, but then the radius and the height aren't staying constant, which is why we had to use this idea of an integral. We're evaluating from a to b, wherever we start to wherever we end, of pi, and then we use the radius function times the height, which was dx, and that radius function was purely just what is the function evaluated at this point, because that gives us a radius. So what we're doing now is we're saying, well, what if it's not a full shape? What if we have something like, in the last video I talked about a bead, right? In this case it's kind of a conical bead in that it's coming to a point, but we have this second line in here, this green line. So we have the black line, we have the green line. So now we are looking at just the area between these figures. We're looking at that green area. We're taking that green little sliver and we are rotating it around the x-axis. And so now we also have, of course, this area down here, so we can see kind of that cone, but it's got really better image would be a cone with the middle cut out. It's a hollow cone, we just have kind of that shell of the cone. But we still have that rotation, so the green is also rotating around. And so we see that that would be its interior, and the green is essentially the negative space. It's the stuff we don't want. So as we've done plenty of times with other problems, right? If we think about, a circle within a circle, a donut, and we want to find this area. Well, we said, well, let's take the larger area and subtract the smaller area. We're going to do the exact same thing here. We're saying we have a larger volume, we have an inner volume that's been removed, so we're going to take the larger volume and we're going to subtract the smaller volume. Now, because we're dealing with a more complex volume, it's not just length times width times height, we have to use this formula kind of twice over. Or another way we can make that a little bit more efficient is to just go ahead and factor off the pi's from both examples, because keep in mind we'd be subtracting a second. A to b pi r squared dx. This would be the volume of the smaller cone. So we could do these as two separate integrals. That would absolutely work. Or we could say, well, let's factor off the pi and then bring these into the same integral, and we'd have r squared, big R squared minus little r squared. And that's exactly the formula that we are given. It is just a subtraction of the two volumes. It's the same exact volume we're finding with our disks, but now we're subtracting the two because we want to get just that shell region, or just that in-between space, that almost bead-like that space there. So we can see that we have the same initial formula. The volume is equal to the integral from a to b of the area dx. Now that area is different. The area is not the whole way across, so we have to find that a little bit more, with a little more complexity. We have to take pi times the larger radius squared minus the smaller radius squared times the height. We can factor the pi off of both of these equations, and we can factor the height out of both of these equations, which allows us to bring it into the same integral. So we do need to make sure that we know the outer and inner radius. That will be important. We got to have those in the correct direction. So what we're going to do is we're going to start with a picture, the same way we have done many times before. Let's jump into an example. Let's find the volume of the solid. Apologies about the color just switching. There's no reason for that other than my computer has some lag time. Find the volume of the solid generated by revolving the region enclosed by, let's take y equals 2 times the square root of x and y equals 2. I need a third one, so let me put a comma in there. So y equals 2 times the square root of x, y equals 2, and x is equal to 0 about the x-axis. Right, so let's start with our picture. 2 square roots of x, just be a square root of x that's a little bit taller. Y is equal to 2, be somewhere up here. And x is equal to 0, meaning this would be our third side. So we're looking at this figure in here. We're revolving that around the x-axis. Okay. So let us think about which of our radius will be the outer and which will be the inner. Well, clearly the one further away is the y is equal to 2. That will be the larger, or the outer radius. The inner will be equal to the 2 square root of 2. We also need to figure out our limits of integration. We're going from where to where. So we know we're starting at 0 very clearly, but where are we finishing? We're finishing at where these two things meet. So I need to set up an equation. When is 2 equal to 2 square roots of x? Well, I can divide the 2 over, and I get x to be really plus or minus 1, but we're clearly looking at only the positive side, so I only need to worry about the 1. So now we can find that volume. We're going to be integrating from 0 to 1. Our pi needs to be there. Then our outer radius would be the 2 squared. Our inner radius is the 2 square root of x squared dx. So let's start to simplify this. We can pull out the pi. We're going to integrate from 0 to 1. 2 squared is 4. Here we'll have 4x dx. Could have also factored off the 4 or the 2 at any point if we wanted to, but I'll go ahead and integrate at this point. So we have 4x minus 2x squared, and we're going to integrate that from 0 to 1. So we have 4 times 1 minus 2 times 1 squared minus 4 times 0 minus 2 times 0 squared. Of course, that's just going to be 0 on the back end. So I'll have pi and 4 minus 2, which is just 2, so we get an area of 2 pi. And that is our answer. That is it. We're done. So pretty straightforward. If we really understand how to find the area, or rather the volume using those disks, the volume using these washers is similar. Let's take a look though. What if we're not rotating simply around the x-axis? So let's do another example. Find the volume of the solid generated by revolving the triangular region bounded by y is equal to 2x, y is equal to 0, and x is equal to 1 about, and we're going to do two different examples, the line line x is equal to 1. So we're going to do two different cases just to see how we can shift away from the x-axis. We can still get an answer using the same ideas. So, volume generated by the triangular region. Well, let's start by picturing what that region looks like. We have y is equal to 2x, we have y is equal to 0, and we have x is equal to 1. So we have this image right here. Well, we need to figure out what we're rotating about first. So let me put that rotation axis on there. We're rotating about the line x is equal to 1. We're rotating about this thing right here. So I didn't write up the formula for this because we should have a pretty good idea of what it's going to look like based on what we're doing with our disks. But we can see here, this is equivalent kind of rotating about the y-axis. So when we're thinking about our radii, we're going to have to think about our radii, the outer and the inner, in terms of the y. Look, if I'm thinking about these things in terms of my y, what I mean by that is my radius is given to me by the x coordinate, right? The amount of change in the x. And that means I need the equation x is equal to is my radius, right? This is my radius. That means I'm going to have an equation in terms of y. So the problem gave me an equation in terms of x. Y is equal to 2x. So the first thing I'm going to do is rearrange this to get the x by itself. And so I'm going to divide my 2 over, and so I'm going to get y over 2 is equal to x. Now that's still not necessarily my radius. We're not just taking that equation directly, because notice this time we're not rotating about the y-axis. We think about the radius. The radius is the distance from this curve to the 1. And so the amount of change there, the larger thing is the 1, and the smaller is the y over 2. That gives me the radius at any point. So if we look at this radius right up in here, it'd be 1 minus that curve. That curve's gotten quite large. Versus down here, the curve is still a very small x value, so 1 minus that very small value, that would give me the radius. So the function is not always going to be your radius. You have to think about what you're rotating about. The radius is the change in the x. Well, how do we find a change in? That is obviously subtraction. Now, because we have a radius in terms of y, we know that the amount of height of the shape is based on our y position, so that would be the dy. But we also need to have the, and I went ahead and wrote it up here, the 2, but I didn't really explain where that came from. We need to have the limits of integration in terms of y is 2. So very clearly this end down here is 0, but how did I know that this was 2? Well, we're looking for when these two things touch. When is this equation, x equals y over 2, equal to an x value of 1? Well, we multiply that 2 over and we get y is equal to 2. And that is how I know that upper limit of integration is equal to 2. Notice we've had to reparameterize everything to be in terms of y because we're rotating about that vertical axis. Everything has been in terms of y. When we were dealing with the rotation about the x-axis, everything was in terms of x. We had x coordinates on the limits, we had x equations in the function, we had a dx, everything's in terms of x. So whatever the line you're rotating about, if you're rotating about a horizontal line, everything's in terms of x. If you're rotating about a vertical line, everything's in terms of y. We need to have those be consistent. Because when we set up our integral, we have y values here from 0 to 2. We have our radius, pi times the radius, 1 minus y over 2 squared. That's in terms of y, and then we have our dy. And so this whole thing is our radius. The whole thing needs to be square. So let's start simplifying this. For starters, I need to plot the pi, but then I also need to multiply out this square. So we'll have 1 minus y over 2 times 2, which is just going to be y, minus, really plus, y squared over 4 dy. Just get that by FOILing out, by distributing out. And now I can take my antiderivative, so I'd have y minus y squared over 2 plus y cubed over 12. And we're going to integrate this from 0 to 2. So we'll have pi 2 minus 2 squared over 2 plus 2 cubed over 12 minus, well then we'd have 0, 0, and 0. So I'm going to just write a 0 back there to indicate that everything else is 0. And so continuing to clean up, we'd have 2 minus 2 squared is 4 over 2 is 2 plus 8 over 12. So the 2's cancel, and then 8 over 12 simplifies to 2/3. We have 2/3 pi. That would be our answer. But I want to do a second part to this because I want to see what happens if we shift that axis a little bit more. So this time we're going to rotate about the line x is equal to 2. This first example was very much just an example in the the disk method that we had been doing. It's being slowly coming up, but remember we didn't have anything taken out of the inside. We weren't dealing with washers. It had just been a disk. Now we'd rotate it in a slightly different way. The radius wasn't just a function because we weren't measuring from 0. We were measuring from 1. So we had to do 1 minus x squared, minus the y over 2 rather, minus the radius. But here, now we're looking at something where we have separation from the axis of rotation. So let me start by drawing out the picture. Again, I know I have a picture right up there, but I want to draw another picture. This was a curve that we were dealing with. We're still dealing with the same curve. It goes from 0 to 2 on the y-axis. It goes from 0 to 1 on the x-axis. We know this shape here is the equation y equals 2x, or that's equal to the whatever we said, the y over 2 that we had before, because it is just a straight line, the y over 2. So we know all the same components, but now we're rotating about this line, x is equal to 2. So we're spinning it this way. There's our other triangles over here, right? Or not really another triangle, but when we rotate it, we'd have this other piece over here as we spin this thing around. So this is very much like the bead sort of picture in my mind, except for it is a triangular bead, but that entire center has been cut out. The only way this thing is attached is through the ring. It is this ring of attachment. And so we do need to figure out this outer and inner radii. And so clearly the outer relationship is this y over 2. That gives me the larger radius. But just like before, we'll call it big R of y, just like before, the radius isn't just a function value because we're not measuring from 0. The radius is measured from the 2. And so we'll have 2 minus y over 2. This radius from here to here, this is what we're rotating about. That entire distance, how do we find the distance between 2 points? We subtract 2, the larger, minus the smaller, minus the y over 2. And then the smaller radius, that would be this distance right here. We're going from 1 to 2. Well, this is actually a consistent radius. This is just 1, but we get that by 2 minus 1. It's just 1, but it's the axis that we're rotating about minus the function value at that point, which is just a 1. So now we have our outer and inner radius. We can set up our integral. We're going from 0 to 2. We have our pi, then our r, big R squared. Let me just go and insert it. The 2 minus y over 2. If my eraser will switch. Apologies. OneNote is a little bit laggy sometimes. All right, let's just scribble it out and maybe it'll erase later. So I'll write in my now it's not doing anything. 2 minus the y over 2 squared. There's our outer radius minus the inner radius, which is 1 squared. And then again, our height is the dy. So we can pull our pi to the front. I'm going to have to multiply this out again. So we're going to have 2 times 2 is 4. Then we multiply the 2. 2 times y over 2 is just y, or negative y. And then we double it to the center. And then we have the y squared over 4 minus 1 dy. And so we could simplify the 4 minus 1 if we wanted to. That'd be pi from 0 to 2 of 3 minus 2y plus y squared over 4 dy. And now we can find our antiderivative, which will be 3y minus y squared plus y cubed over 12. We're going to integrate that from 0 to 2. The squared should not be on the pi. That was a 2 on the integral. That 2 should be on the integral, not on the squared. So get rid of that squared there. And so now if we plug in, we'll have 3 times 2 minus 2 squared plus 2 cubed over 12 minus, and again we plug 0 in for all it is, it's just 0. So we'll have pi times 6 minus 4 plus 2 cubed is 8 over 12 is 8 over 12. So pi times 2 plus 8 over 12. and we can get a common denominator if we want to clean it up a little bit. Really, the 8 over 12 cleans up to 2/3, same way we said before. So 2 plus 2/3 would be 8/3. So we get 8/3 pi, and that would be our answer. Our units would be cubed. Of course, it's a volume, but we don't know what they are, so that is my answer. So very, very similar to our disks, but we have an outer and inner disk now. We have to take out that inner disk. We also need to be really careful that we know what axis we're revolving around. If we're revolving around the x-axis, what we've seen in a couple examples now, everything is in terms of x. If we're revolving around the y-axis or any vertical axis, everything is in terms of y. We need to make sure that we are understanding the radius. The radius is not necessarily just a function if we're not rotating around the x or y axis itself. We might have to subtract or add some things to get the full radius. In the next video, we will be looking at our conical shells, and these will help us do the same sort of problem that we've been working with the washers. Now, one or the other is usually easier depending on what we're given, how the problem is set up. This one was not a very hard problem to reparameterize everything in terms of y, right? We had to write everything in terms of y because we were rotating around that vertical axis. But what if we have something that's harder to solve for the x? Well, then it would be nice to have another way to view these things, and that's what the shells or the shell method will do for us.